Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD heat transfer analysis through a microchannel heat exchanger. This is a special type of shell fin heat exchanger, and in this case heat transfer takes place in lateral confinement, and the shell is having very less size. Generally the shell size is less than 1 millimeter. To understand the geometry of this model, let us cut it from specific plane. Let us cut it from front plane and see the geometry. So from this end, we'll provide freon at a temperature of 70 degrees centigrade. Right, you can see here. It will pass through the small channels. Channel size is less than 1 millimeter. So hot freon will be passing from these small shells, or you can say small micro channels, and it will be accumulated at the right hand side here itself, right? And from Z direction will provide air at a higher rate, so freon will be suffering change of phase and it will be accumulated at this location, and as its temperature is falling down, it has a tendency to go down and it will be coming from these different channels at the bottom side, right? From these openings freon will be passing, and again while passing the backward direction it will suffer a change of phase, and finally at this exit opening we'll have cold freon, right? I'll repeat this one again. From this opening we'll provide hot freon at a temperature of 70 degrees centigrade, and while passing from these small channels it will suffer change of phases, as from Z direction will provide air at high velocity, so it will be cooled, and at the right hand side it will be accumulated and its temperature will fall down, and again it will pass through the small channels from the downside, and at the exit it will be collected at this location, right? Let us have a complete view of this model. Now for starting this simulation, we need to create a flow simulation environment, and that will be created with Wizard itself. Let us consider this project name as project 1. Next to that, we need to select units. We are considering SI units, and as it is a heat transfer problem, so we'll consider temperature to be in degrees Celsius as usual. Next to that, we need to select what type of analysis it is. It is an external analysis because we will provide air from outside at a specific velocity, and from physical features it will be heat conduction in solids, and gravity will be involved. So the direction of gravity will be y as indicated by this green arrow in the downside, and gravity will be minus 9.81 meter per second square along y direction. Along Z it will be 0. Next to that, we need to select different fluids. Through this microchannel heat exchanger we'll provide freon at 70 degree. It will be in gaseous phase, so we're considering R123 as the main fluid passing through these micro channels, and we'll consider another fluid, air, which will be utilized for cooling this freon gas. So you considered air and freon as two different fluids. Next to that, materials. In this case, we're considering materials are made up of aluminum alloys, aluminum 6061 alloys. We're considering default roughness parameters, and finally we need to select thermodynamic parameters as pressure as 1021325 Pascal, and temperature we'll consider as 20 degrees centigrade. And solid parameters, again it will be 20 degrees centigrade. And in this case we'll consider air will be traveling from Z direction. Let us see the direction here itself. Air will be passing at a specific velocity of 40 meters per second in Z direction. You see the direction, that means air will be passing from this direction through the fence. So the direction of air is Z, and it will be moving with a velocity of 40 meters per second. Let us finish this. You can see this is the computational domain. It is suggested to have a very small volume of computational domain to reduce the calculation time. So let us edit this computational domain. While editing this one, we should think that all parts of this model should be inside this domain. Nothing should be outside. From front plane, it is okay. Let us see it from other planes also. Computational domain is ready. Green check. So this is our model. Let us hide computational domain. Next to that, we need to select our fluid domains. We have two fluids. For showing the fluid subdomains, let us have a segmented view of this model. Let's cut it from front plane and fluid subdomains. Insert fluid subdomain. Freon at a temperature of 70 degrees centigrade will be passing from this opening. This is fluid subdomain of freon, and air will be passing from opposite z direction. It will be passing across this fins. So this is subdomain for freon, and solid materials we have already defined. It is made up of aluminum alloys. Next to that, we need to apply boundary conditions, right? Insert boundary conditions, and we'll provide freon from this opening at a higher temperature and low velocity, right? Let's consider that inlet velocity of freon as 0.01 meter per second. Let us see thermodynamic parameters. At 70 degrees centigrade, from here freon will be passing, right? Let us accept this one. Another boundary condition to be applied at the exit opening. It will be atmospheric pressure. So insert boundary conditions. It will be atmospheric pressure at the exit location, right? Let us select this one. Environmental pressure at the exit location. Accept this one with green check. Both the boundary conditions have been applied. Next to that, we need to find some goals. Our main aim is to find temperature at the exit opening. So we'll select a surface goal at the exit surface. Goals. Insert surface goals, and it will be average temperature of fluid at the exit surface. Green check. We have selected the goal. Now let us run this. Iterations have already started. Let the iterations move on. You can see our results from Solar window itself. This one is showing temperature distribution from right plane, and temperature is varying in between 20 to 70 degrees centigrade. Initially at the exit location, temperature is 20.053 degrees centigrade. Let us see this distribution from different plane also, from front plane. And we want to see temperature distribution, temperature of fluid from front plane. Initially, the temperature of freon is 70 degrees centigrade. It is showing. It is a steady state heat transfer analysis. So finally, you will see the temperature distribution through these different locations, right? You can see the goal also, same time. As time is approaching, you can see the temperature of freon is decreasing. And you can see here minimum temperature at this moment is 15.94 degrees centigrade. So temperature is varying as time is passing. You can see temperature of freon from two different planes, front plane and right plane. This one is the right view, and you can see here through the micro channels temperature is at this moment it is very high. It is in the range of 70 degrees centigrade approximately, and surrounding this heat exchanger we are having different fins, and across these fins we are providing air at a high velocity of 40 meter per second. Now you can see that minimum temperature is 14.16 degrees centigrade, right? It's changing. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis, right? You can see here near the fins, here at this location, temperature is coming down. It is 13.64 degrees centigrade at these locations. At the right hand side of this heat exchanger, temperature is less. It is 13.62 degrees centigrade at this moment. Near the fins at the right hand side. Now minimum temperature you can see at this moment it is 13.19 degrees centigrade. So as time is passing, temperature at the fins it is reducing. Finally, temperature at the exit of this heat exchanger also it will reduce. You can see sulfur is finished and our result is conversed, and you can see the final temperature at the exit of this microchannel heat exchanger is 20.008 degrees centigrade, and at different locations you can see the temperature. So for this is the entry of freon. In this case temperature is high, which is indicated by red color, and at the extreme right hand side temperature of that one has come down. Again at the left hand side also here temperature is less, right? And you can see here through the micro channels when freon was passing from left hand side to right hand side, the temperature is in the green zone, right? Let us close it. Next to that, when you see temperature distribution through different locations, and we'll see different cut plots also, right? Let us see the results from here, and what you see cut plots, insert cut plots, and what you see temperature distribution through front plane. Instead of pressure, when you see temperature distribution, temperature of fluid through front plane. Let's see this one. This is temperature distribution through the front end. You can see here at the entry level temperature is very high, right? Let us have an animation of this one. Let us play. Next to that, we want to see temperature distribution through all surfaces. It will be surface plots, insert surface plots, and we want to see temperature distribution using all faces. You can see temperature distribution at different surfaces, right? At the right hand side, temperature is in the range of 25 to 32 degrees centigrade here, and at the exit location temperature you can see it is very less across the surface only. But if you see inside, it will be different. Next to that, you want to see our results from goal plots, which one we have already seen from the solar window itself. Anyway, let us see results from goal plots. Insert goal plots, and we have selected only one goal, this average temperature fluid at the exit location. Let us see it. We can export that one to Excel also. Let us see the graph. It is showing that initially temperature at the exit location was 20.005 degrees centigrade, and after 108 numbers of iterations it has come down to 20.007 degrees centigrade. So this is not the main aim. Our aim was to see the temperature distribution through the fins, and while seeing the temperature distribution through front plane, we have seen that temperature near the fins were from 13 to 15 degrees centigrade. That means near the fins, temperature of air has been reduced. Let us see that model again. That from this opening, we have provided freon at a temperature of 17 degrees centigrade, and at the exit location, you can see the temperature of freon has come down to 20 degrees centigrade. And in this case, the phase of freon has been changed. 70 degrees centigrade, freon was in gaseous stage. So that gaseous stage has been converted to liquid phase, and near the fins we could see the temperature distribution less than 20 degrees centigrade. It was in the range of 13 to 15 degrees centigrade. Instead of stopping it here, we can go for some kind of parametric study. We can see at different velocities of air what may be the temperature distribution near the fins. Then finally, based on our specific requirement, we can go for some optimization. Okay, so this one will conclude our analysis. So we are not going for some kind of parametric study and optimization. That can be done any other time. Okay, thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.